My name is Pakdam Tibekabe. I'm from Cheikh Anta Diop University in Senegal. Today I'm going to give a talk on the Diophantine equation summation from K of K, which is going from 1 to 5 of Fnk, which is equal to 2 to the power A. My presentation or my talk will be subdivided in 5. First of all, I will give the abstract of this paper, and secondary, I will give an introduction, and in third position, I will give an auxiliary result, and in fourth position, I will give the main result, and in the last section, I will give the table of all representation of all powers of 2, which can be written as a sum of 5 Fibonacci numbers. In terms of abstract, if we consider Fn the Fibonacci sequence defined by F naught is equal to 0, F1 is equal to 1, and Fn plus 2, which is equal to Fn plus 1 plus Fn for all n greater or equal to 0. In this paper, in the one hand, we have determined all the powers of 2, which are sums of 5 Fibonacci numbers, with a few exceptions that we characterize. And in the other hand, we have established a conjecture showing that such equation admits infinitely many solutions. As introduction, we know that solving Diophantine equations fascinates many mathematicians, specializing in number theory. And there are several methods of solving those equations. Among them, the most faithful is surely the one which associates the linear forms of logarithms and some calculation with continued functions. We know that there are only 3 Fibonacci numbers that are powers of 2, and a proof of this fact follows from Carmichael's primitive divisor theorem, which states that for n greater than 12, the nth Fibonacci number Fn has at least one prime factor, which is not a factor of any previous Fibonacci numbers. And we know that there are 9 powers of 2 in the sum of 2 Fibonacci numbers, and 15 in the sum of 3 Fibonacci numbers, and 60 in the sum of 4 Fibonacci numbers. First of all, the goal when I start writing this paper was to try to see if I can find a sequence which describes the distribution of powers of 2 in the Diophantine equation involving Fibonacci numbers. That was the first goal of this paper when I start writing it. And in this paper, we show that there are exactly 106 powers of 2 in the sum of 5 Fibonacci numbers. That is, we solve this equation 1. And this paper is subdivided as follows. In section 2, we introduce auxiliary results that we use in section 3 to prove the main theorem of this paper, which can be stated below. All non-trivial solutions of the Diophantine equation 1 in positive integers n1, n2, n3, n4, n5, and p, with n1 greater or equal to n2 greater than or equal to dash dash n5 are listed in section 6. Okay, in auxiliary results, we can say that in this section we give some important known definition and properties, theorems, and lemmas. We know that for an algebraic number gamma, we define its measure by the following identity, which is given by this, where gamma I are the roots of fx, which is equal to ad product from I, which is going from 1 to d, x minus gamma I, the minimal polynomial of gamma. Let us define another height deduced from the last one called the absolute logarithmic height, which is defined like this. When we have a non-algebraic number of degree t over on Q, where the minimal polynomial on Z is f of x, we will denote the absolute logarithmic height like this, as we can see there, which is called the usual logarithmic absolute height of gamma. And we know that there are some properties, of the logarithmic heights, which can be defined like this. And the nth Fibonacci numbers can be represented by this, which is alpha n minus beta n all out of the root square of 5 for all n greater or equal to 0, where alpha and beta are defined of this by this. And the following inequalities are well known, which and hold for n greater or equal to 1 and can be proven by induction on n. The following lemma is deduced from corollary 2.3 of math paper entitled An Explicit Lower Bound for an homogeneous rational linear form in the logarithm of algebraic number. And the math theorem can be stated like this. When we have gamma 1 up to gamma s, the real all real algebraic numbers, and b1, b2 up to bs, the non-zero rational numbers, let d be the degree of the number field q of gamma 1 up to gamma s over q, and let a, j be a positive real number satisfying this condition. And when we assume that b is greater or equal to this expression, and if this expression is not equal to 1, then we will have this approximation. The following two lemmas are due to Jugela and Peto and Legendre respectively. For a real number x, we write the norm of x, which is equal to this for the distance of x to the nearest integer. And the lemma of Jugela and Peto can be stated like this. When we consider m a positive integer and p by q the convergence of the continued fraction expression of k or kappa, such that q is greater than or equal to 6m, and let a be mu real numbers such that a greater or equal to 0 and b greater of 1. And when we consider epsilon, which is equal to this, and if epsilon is greater than 0, then there is no solution of this inequality in integers m and n with this inequality. And the lemma of Legendre can be stated like this. Let tau be a real number such that x and y are integers such that this condition is verified. Then x out of 1, y is equal to pk out of qk, which is a convergent of 2. And further, we have also this inequality. The plane. In the main result, we will first try to find the bounding. We will first try to bound n. If we assume that this condition, this inequality holds, and we will first try to find the relation between n1 and a. When we combine equation 1 with the well-known inequality fn less than or equal to alpha n minus 1, for all n greater or equal to 1, one gets this inequality. And we will have all this, which is less than or equal to this, and finally, which will be less than 2 to the power n1 plus n plus 1. Hence, from this inequality we obtained previously, we will find directly that a is less than or equal to n1. This inequality will help us to calculate some parameters. When we rewrite equation 1 and taking absolute values on both sides, we will get this inequality in which we use fn less than or equal to alpha to the power n minus 1. When we divide both sides of the above equation by alpha n1 out of by the root square of 5, we will get this inequality. And when we take in the account the condition, this inequality, we will get the equation 2. And we will now apply the Matthew theorem with the following parameters. T will equal to 3, and gamma 1 is equal to 2, gamma 2 is equal to alpha, gamma 3 is equal to the root square of 5, b1 is equal to a, b2 is equal to minus n, and b3 is equal to 1. Since we know that all those algebraic numbers belongs to the field, belong to k, which is equal to q of the root square of 5, we can take d, which is equal to 2. And before applying the Matthew theorem, we have to check the last condition, which means that the left-hand side of equation 2 will not be equal to 0. We will do this by contradiction. First, we will see if it were not 0, we will then get 2 to the power a times the root square of 5, which is equal to alpha n. When we square the previous relation, we will get this, and this will imply that alpha to the power 2n belongs Z, which is impossible. And then this implies that the lambda 1 is not equal to 0. And applying the formula of calculation of logarithmic height of gamma 1, gamma 2, and gamma 3, we will get this, from which we can deduce a1, a2, and a3. Since we know that a is less than n1 plus 1, and B is equal to the max of absolute value of B1, B2, and B3 is equal to N. Mathview's result will inform us that we will have this equation 3, when C1 is equal to this expression. And when we take the log in inequality 2, we will get log of lambda 1, absolute value of lambda 1 is less than this. And taking log in inequality 3, we will also get this. And when we compare those two inequalities, we will get equation 4. We will now consider a second linear form in logarithmic. And we will do also the same thing. We will rewrite the equation 1 and take absolute value on both sides, and the fact that beta is equal to this, and we'll get directly this inequality. And when we divide both sides of the inequality by this, we will obtain equation 5. We will apply again Matthew theorem the second times with the following data that you can see there. And the left-hand side of 5 is not 0. Otherwise, we will get the relation 2 to the power a root square of 5 is equal to alpha n1 plus alpha n2. And when we conjugate equation 6 in the field q of the root square of 5, we will get this equation 7. And when we combine equation 6 and equation 7, we will get this inequality, which is impossible since we know that n1 is greater than 400. Hence, lambda 2 is not equal to 0. We know that the logarithmic height of gamma 1 is equal to log of 2, and logarithmic height of gamma 2 is equal to half of log of alpha. And let us now estimate the logarithmic height of gamma 3. But before to do that, we first prove that gamma 3 is less than the root square of 5, and then gamma 3 to the power minus 1, or the inverse of gamma 3 will be less than 2 out of 2 under root square of 5. So the absolute value of log of gamma 3 will be less than 1. Using properties of logarithmic height and stated in section 2, we will have that the logarithmic height of gamma 3 will be less than this in this equality. Hence, we can take A3, which is equal to this according to the definition, and applying Matthew theorem, we will get this expression where we know that C2 is equal to this. And finally, from 5, we will get this equation 8, which is the bound, which will give us the bound of n1 minus n3. And putting relation 4 in the right-hand side of equation 8, we will get this expression 9. And we will now consider the fifth and last theorem, and the last linear form in logarithmic. We omit the case of the third and the fourth linear form in logarithmic because they will be done similarly. The procedure is same. Then we'll try to omit it and just do the last and try to find the last linear form in logarithmic. And rewriting equation 1 once again by separating large terms and small terms, we will get this equality. And when we will take the absolute value in on both sides, we will get this relation. And dividing the both sides of the above a relation by the first term of the right-hand side of the previous equation, we get lambda 5, which is less than 3 out of 3 under alpha to the power n1. And in the last application of Matthew theorem, we will get the following with the following parameters. We will finally get that. We will finally prove that we will first in those equations we are trying to prove that lambda 5 is not equal to 0, since it is one of the hypotheses to be verified before to apply Matthew theorem. And we did it by contradiction. As we can take now A1, A2, and B, which is equal to this. And when we will try to estimate the logarithmic height of this algebraic numbers gamma 3, we can see that gamma 3 is also less than the root square of 5, and the inverse of gamma 3 will be also less than the root square of 5. Hence, the absolute value of log of gamma 3 is less than 1. Then the logarithmic height of gamma 3 will be less than or equal to this. And since we can now deduce A3, which will be equal to 5 plus n1 minus n2 log of alpha, plus n1 minus n3 log of alpha, plus n1 minus n4 log of alpha, plus n1 minus n5 log of alpha. Then the lower bound of the left-hand side of 10 will be equal to this, where C4 is equal to this. So we can finally obtain the equation 12. And using 4 and 9 in the rightmost term of the above inequality 11, And performing the respective calculation with the help of Mathematica, we finally found that N1 is less than 1.6 times 10 to the power 73. We recall that what we have proven now in terms of lemma. If N1, N2, N3, N4, N5, and A is a positive solution for equation 1 with those conditions, then we will have this inequality which will hold. Now we will try to reduce the bound on N. To do this, the goal of this section is to reduce the upper bound on N to a size that can be handled. To do this, we shall use lemma 3.5 times. Let us consider this function. From equation 13 and 2, we can write this like we can write equation 13 like this. 1 minus expo z1 will be less than 11.5 under alpha to the power n1 minus n2. Associating 1 and Binet's formula for the Fibonacci sequence, we will have this inequality, which also will give us this, which leads to z1 greater than 0. And this result together with 14 will give us this inequality. Replacing 13 in the inequality and dividing both sides of the resulting inequality by log of alpha, we will get this equation 15. And we put finally tau, which is equal to this, mu is equal to this, A is equal to 24, and B is equal to alpha. And tau it will be an irrational number. We also put M, which is equal to 1.6 times 10 to the power 73, which is an upper bound on A by lemma 3.2 applied to inequality. Then we will finally get that N minus N2 will be less than log of A Q out shows under alpha, epsilon. Sorry. Where Q is greater than 6m is the denominator of a convergent of the continued fraction of 2, such that epsilon is equal to this. A computation with such math revealed that if all those numbers, if n1, n2, n3, n4, and n5, and A is a possible solution of equation 1, then we will get n1 minus n2, which belong to this interval 0 to 367. We will now consider a second function derived from 5. We will do the same thing, and putting the expression of z2 in the above inequality and arguing as in 15, we will obtain this equation, this inequality 17. And as before, we will also take the same parameters, but the exception in this equation will be what? In this case will be what? For this case, when we apply, for the case when n1 minus n2 belongs to 2 and 6, when we apply lemma 3.2 to the expression 17, the corresponding parameter mu appearing in a lemma 3.2 will be equal to this. And in those both cases, the parameters tau and mu are linearly dependent, which yield that the corresponding value of epsilon from lemma 3.2 is always negative, and therefore the reduction method is not useful for reducing the bound on n in those instances. For this, we need to treat those cases differently. However, when we can see that if t is equal to 2 and 6, the resulting inequality from 17 and has the shape this inequality with tau being irrational number and x and y belong to z. Then, when we use the properties of convergence of the continued fraction to obtain a non-trivial lower bound for this absolute value, we will see that for n1 minus n2 is equal to 2, and from equation 17, we will get this equation 18. And if this is a continued fraction of tau, and we do not PQ under QK, the Kef convergent, and by lemma 3.3, we know that A is less than 1.6 times 10 to the power 73, and furthermore, we will get this. So from the properties of continued fraction, we will obtain this equation inequality 19. And comparing equation 18 and 19, we will get this inequality, and taking both log on both sides, we will get finally that n1 minus n3 is less than 367. And in order to avoid the repetition, we already omit the details for the case n1 minus n2 is equal to 6. Here we get again this inequality, and we will do the same thing, and in finally we will get that n1 minus n5, which is equal to less than 369. And finally we will use 10 in order to improve the upper bound on n1, and we put z5 is equal to this. We will do the same procedure, and finally we will get that n1 is less than 369, and which is also of course false, because our assumption is that n1 will be greater than 400, and this ends the proof of our main theorem. And in this last section we will find the table of all representation, all solution of this equation 1. All solution of equation 1, I want to say that it is all powers of 2 that can be expressed as or that can be written as sum of 5 Fibonacci numbers. We have 106 solution. And we have also established the following conjecture on the Diophantine equation written as a final sum of Fibonacci numbers. If Fn represents the n Fibonacci number and R the number of Fibonacci numbers in the exponential Diophantine equation 23 in positive integer n1, n2 up to nr, and P with n1 greater or equal to n2 greater or equal to ... nr, then the equation 23 has infinitely many solutions. Thank you for your attention. Those and we have that now the bibliography of what we have used now. Thanks.